Today's podcast, I look at some of the applications for the op amp. We talked about the basic what the function was last time, so let's just review that a little bit here. So the important point is we're going to have feedback, and feedback is a connection between V out and one of the inputs, either the non-inverting input V plus or the inverting input V minus. And so if we have that feedback, then the op amp behaves in a certain way. So once we identify those feedback, and we make these assumptions, the ideal op amp, and then there's these basic rules. And the basic rules are no current flows into the inputs, so no current flows into V plus or V minus at the op amp. And then if there's feedback that it's going to work, the feedback's it's going to change the output until V plus is equal to V minus, or the non-inverting input voltage is the same as the inverting input voltage. And so that's the basic function. We said there's a basic cookbook. How do you go about doing this? You're going to check for feedback. If there's no feedback, you're going to assume there's no current into the inputs. You're going to determine V plus or V minus, whichever is not connected to the feedback path. You're going to assume V plus equals V minus, find the current in. Then you can use Kirchhoff's junction rule and say, well, if there's no current into the non-inverting input, we have current going to the left, then we must have current coming from the feedback path. And we can find what that current is, and then we can find the change in voltage across the feedback resistor, and then we can find V out. So that's the basic plan. So let's apply that to a few circuits. The first we're going to look at is the inverting amplifier. Is there feedback? Yes, there's feedback. There's a connection between the output and the inverting input in this case. So there is feedback. We're going to assume no current into V plus or V minus. So we're going to find V plus, right? That's the input not connected to feedback. That's hooked to ground, so that's going to be 0 volts. We can assume V minus equals V plus. That's 0. V plus is equal to 0, so V minus is going to equal to 0. We can find in, right? We just use Ohm's law. We know the change in potential across the resistor, Vin minus 0, divided by Rin. That's going to give us the current into the op amp, or inverting input. Now we can find I feedback. We can just apply Kirchhoff's junction rule. No current goes into the input. We have In, so feedback must equal the input current. So that's what we calculated before. It's just going to be Vin over Rin. So we can find the change in voltage, right? Now we're just going to use Ohm's law. We know the current through the feedback resistor, so we can find the change in potential. We know current flows from high to low potential, so this is going to be the plus side on the left, the lower potential side on the right. And we can find out what that value is. It's just the current times RF. And then we can find V out, which is just going to be what's the potential at the inverting input plus the change in potential across the feedback. That's what V out's going to be. So in this case, the voltage at the inverting input is 0. We know the change in potential across the feedback resistor, which in this case is going to also equal V out. And you can see that it's an inverting amplifier in that it's Vin multiplied by some constant. That's just the ratio of the feedback resistor and the input resistor. And it's inverting because it's minus. So if I put a positive input voltage, I'm going to get a negative output voltage. Or if I put in a negative input voltage, I'm going to get a positive output voltage. So that's the inverting amplifier. So now we can write down sort of the characteristics of this circuit, right? V out is going to be minus RF over Rin times Vin. The gain, which is just V out over Vin, is just going to be the ratio of the resistors and a minus sign. Okay, let's look at the non-inverting amplifier, right? In some cases, you don't want it to be inverting. You want it to be a non-inverting amplifier. So we're going to go through the same steps. Is there feedback? Yes. There's a connection between the inverting input and the output. We're going to assume no currents into Vin or into the input, non-inverting input and the inverting input. We can find V plus. V plus, well, what is V plus going to be? It's just going to be equal to the input voltage. So now we assume V minus is equal to V plus, which is equal to the input voltage. So we got that. We can find In using Ohm's law. We know that Vin is just going to be, or V minus is going to be Vin. To ground, there's going to be a change in potential across R1. We can find the current In. We can find the feedback current using Kirchhoff's junction rule. Feedback current must equal the input current because there's no current going into the inverting input. Then we can find the change in potential across R2, or the feedback resistor. It's just going to be the current times the feedback resistor. So we calculated the current before as Vn over R1 times R2. We know that the potential goes from high, or the current flows from high to low potential. So we know the left side is going to be the low side, the right side is going to be the high side. And then we can find V out is just going to be what's V minus, that's V in. And we're going to go up in potential plus the change in potential across the feedback resistor, which in this case is R2 over R1 times V in. And we get some constant that depends on R1 and R2 times the input voltage. And so there's no minus sign, it's not inverting, but we get an output that's proportional to the input voltage. So we can summarize those results. V out is just going to be what we just calculated, R1 plus R2 over R2 times V in, so that we can put whatever we want and get a V out. The gain is just going to be the ratio of those resistance values. So again, this is a non-inverting amplifier. Okay, let's look at a summing amplifier. So here we have V1, V2, V3. We have 3 different inputs, and they're all attached to 3 different resistors, and they all come into the inverting input. So we're going to apply our cookbook. Is there feedback? Yes. There's no current into the inputs. So let's find V plus, the one not connected to the feedback. That's 0. It's hooked to ground. We know V minus is going to be V plus, which we just said was 0. So now we can find the change in potential across each of those resistors, R1, R2, and R3. Right, and we can use Ohm's law and just add up those currents so we can figure out the input current. We can find the feedback current using Kirchhoff's junction rule. I out equals the feedback equals I in, which we just calculated. And then we can find the change in potential across the feedback. So that's the magnitude of the potential. We know the potential current flows from high to low, so in this case it goes from left to right. And so then we can find what's the output voltage. It's going to be V minus, which in this case is 0, minus the change in potential across the feedback resistors. And so we're going to get a minus this current times the feedback resistor. So in the end, we can write that V out is equal to some complicated thing that depends on R1, R2, R3, and the input voltages. But we can look at a simplifying case where R1 equals R2 equals R3, right? In which case V out is then just minus V1 plus V2 plus V3 times some gain factor, RF, over whatever that input resistor is, right? And so then this is just a summing amplifier. It sums the voltages V1, V2, and V3 with some kind of gain factor, but the main point is you can add up those voltages. So this might, if you want to make a complicated sine wave, one with 2 different frequencies, you could put in one at 100 hertz, one at 200 hertz, and this is a way that you could add those signals together.